Hey guys, hey guys, how are you doing? I hope you're great. It's good to be back. So, in the last video, we described the places where electrons could be in an atom. That is, we talked about orbitals, and we used four numbers in order to describe the orbitals. Now, in this video, we're going to see how we place electrons in the orbitals. For instance, let's consider the hydrogen atom. The hydrogen atom has only one electron. In which orbital is that electron? In the 4s, in the 2s, in the 2p? We talked about so many orbitals. In which orbital does that electron is? And then let's consider hydrogen, helium, lithium. Lithium has 3 electrons. Where are these 3 electrons? Are they all in the same orbital? And if so, in what order do we place electrons in which orbitals? And how many electrons can each orbital have? And we are going to answer that with the help of 3 rules, which are going to see one after the other. And after we finish all these rules, we will be able to make the electron configuration of every atom. So let's get going. First of all, the Pauli exclusion principle. What Pauli said, he was a chemist, and using this, we can calculate how many electrons can each cell, subcell, and orbital fit. In an atom or molecule, no 2 electrons can have the same 4 electronic quantum numbers. As an orbital can contain a maximum of only 2 electrons, the 2 electrons must have opposing spins. So I understand 2 things. First of all, an orbital has 3 of the 4 quantum numbers the same. For instance, the orbital 2s has 1s has 1, 0, 0, and this is the orbital 1s. So it has the first 3 quantum numbers the same. And then we have 2 different possible ms numbers. So cell K, N1, has 1 subcell, L0, in which 1s orbital corresponds. Inside, we can how many electrons can we put in one orbital? We can put 2. Why? Because each electron must have their own unique set of quantum numbers. That is, if one electron has the set 1, 0, 0 plus half, the other must have 1, 0, 0 minus half. So I can have any other electron, because any other electron that would get in this orbital would have the same that or that. And according to Pauli exclusion, we can have electrons with the same 4 electronic quantum numbers. Therefore, an orbital can contain a maximum of 2 electrons. And these 2 electrons have what? Opposing spins. This has positive and this has negative. We said that the ms number shows us the spin of the electron. Now let's look at the cell 2, L cell. How many subcells has? We'll look at the L number, can be 0 or 1. The ml 0, and for 1, minus 1, 0, plus 1. This is 2s, and this is 2p. Okay, we got 3 2p's. Now, how many electrons can each orbital take? 2. So we got 2, 4, the 2s can take up how many? 2 electrons, and the 2p can contain 2, 4, 6 electrons. And the cell L can take 2 plus 6, 8 electrons. So now we can calculate using that how many electrons can each cell, subcell, and orbital can fit. Alright, and now that we know how many electrons can each orbital have, we need to answer a question. In which orbitals will we place them? For instance, hydrogen has only 1 electron. Where is that electron going to be placed? In the 1s, in the 2s, in the 4f? Where? In which order we start filling electrons? So The lowest energy principle answers that question. It states that electrons fill orbitals starting at the lowest available energy states before filling higher states. And so you're going to ask, how can I determine which orbital has the lowest energy and which has the highest energy? According to these two rules. Between two subcells, the one with the lowest energy is the one with the lowest sum of the first two quantum numbers. And if I have the same sum, like 4s, which is 4 plus 1, 5, 3 plus 2, and 3p, 3 plus 2, 5, they have the same sum of n plus l, which has the lowest energy, the one with the lowest n number, therefore 3p. And if we start making this mathematics, we see that we got this. So the lowest is the 1s, because it has 1 plus 0, 1, then 2 plus s, 2 plus 0, 2, 2p, 2 plus 1, 3, 3 plus 0, 3. But between those two, which have the same n plus l number, 2p has the lowest energy because of that, because it has the lowest n number. And therefore, by making all this mathematics, we see that this is the order which will fill electrons. So, we start placing 2 electrons in the 1s, then 2 electrons in the 2s. We show that a p can have how many electrons? Can fit 6 electrons. Then we place 2 electrons in the 3s, then 6 electrons in the 3p, then 2 electrons in the 4s, then 10 electrons in the 3d, because it has 5 orbitals. The 3d has 5 orbitals. The 4p has 1 orbital, therefore can take up to 2 electrons, and we start filling in this order. And now you're going to ask, how I'm going to remember the order of the energy? I'm going to calculate that all the time? No. This is why we got a mnemonic rule. What is a mnemonic? It is a tool to help remember facts or a large amount of information. So there is a rule, a mnemonic rule, in order to remember the order in which we complete. First of all, we write the numbers of the n. So we got the cell 1, 2, 3, 4, 5. And then we write next to it how many subsets we're going to have. We're going to have the 1s, the 2s, the 2p, 3s, 3p, 3d, 4s, 4p. And we write them to make that table. We usually stop in the 4, maybe in the 5th. And then we put these diagonal arrows, which go up and up. And according to this, we fill. So first we start with the 1s, then we go what? Here, it goes to the 2s, then I'm going here, 2p, 3s, then I'm going up here, 3p. I'm not going to fill the 3d. First, I'm going to fill the 4s, and after the 4s is filled with electrons, then I'm going to go to the 3d, 4p, 5s, then 4d, 5p, 6s, then 4f, 5d, 6p, 7s, etc., etc. This is the order of subcell filling. Okay, and now let's see some examples. What's that? Oh yes, hydrogen has how many electrons? 1. Therefore, it's going to go to the 1s. It's going to have 1 electron in the 1s, and this is how we write it. Helium has 2 electrons, therefore it will go to the 1s. Lithium now has 3 electrons. The first 2 will go to the 1s, but the 1s cannot take more than 2 electrons. Therefore, the third electron must go somewhere else. Where is it going to go? I got 1s, then 2s. Therefore, it's going to go to the 2s. Same beryllium, the same for boron. And this way, we start filling our orbitals. Now let's see a more complex example. Iron. Iron is a 26th. So you see, we first make this table, all right, and then we start filling orbitals. First we will start with 1s. How many takes? 2. Okay. So out of the 26, I have now added 2. Therefore, I now must add 24 more. Then I'm going to fill the 2s. I'm going to put 2 in the 2s and 6 in the 2p. Minus 2 minus 6, I'm 16 left. I need to put 16 more. So this 2p, then I'm going to fill the 3s. How much it can take? 2. I'm putting 2 and then I can see that I got 14 left. So I remember 1s2, then 2s2, the arrows, you know, I'm pointing the arrows now, I'm in my mind. This, then this, then this, and then this. So then I'm going to put in the 3p, how much can it take? 6 in the 3p, and then after the 3p, what goes? The 4s. Sorry. Give me a second to make this disappear. Okay. So I'm putting 6 in the 3p6, in the 3p, therefore I now got 6 electrons, and I got 8 electrons left. After the 3p, the 4s, I fill the 4s. And I'm putting 2 electrons, therefore I got 6 more left. And if I make the arrows again here, you will see that 2p3s, then 3p4s, and then 3d. Now I'm going to fill the 3d. With it can take the 3d can take up to 10 electrons, and I have only 6 left. Therefore, this is the electronic configuration of iron. And now someone asks you to write down the electronic configuration of iron. How are you going to write it? I mean, you will write it like this, and this is the correct way of writing it. Some people and some textbooks find it correct, but in my scientific opinion, it is not. Anyways, they write here the orbitals in the way we fill them, in the order that we fill them. Therefore, they write 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d6. This is actually incorrect. Why? Because after the 3d takes electrons, it is now in a lower energy level than the 4s. When it was empty, when the 3d and the 4s was empty out of electrons, 4s had what? Had a lower energy level than 3d. But after they got filled with electron, 3d is in a lower energy level than 4s. And therefore the outer cell of iron that contains electron at this point is the 4s. And this is why this way of writing is correct. Okay. Now let's consider the electronic structure of an ion, the ion of iron. It has 2 electrons less than the iron atom here. So where are these going 2 electrons be removed from? The 3d6 or the 4s2? Even though I filled the 3d6 last, the 4s was the outer electron cell, and therefore they will be removed from there. Now, you could make a really big mistake. What is this mistake? This is the correct electronic configuration for this ion. But if you try making the electron configuration for the iron, trying to put 24 electrons, you know what would be the results? Let me write you down that pretty quickly. You would have 1s2, then you would put 2s2, then 2p6, then 3s2, then 3p6, 3d, I'm leaving it blank because I need to fill the 4s first, 4s, 2, and now I got 4 left for the 3D. So if you were trying to make the electron configuration for this ion, considering that it has 24 electrons, you would be incorrect, because you would have this as a result. So what we do, we write down the electron configuration for the complete iron atom, like that. And then, from the outer cell, we take from there the number of electrons. So this has 2 electrons less. Where are they going to be taken from? From the outer cell, therefore from the 4s2. And I will have this resulting correct electron configuration. Alright, and now I told you about 3 rules. You're going to be wondering, okay, I can make electron configuration knowing these 2 rules. So where is that 3rd rule? Why do I need this? You're going to see. For instance, I want to put 4 electrons in the 2p subcell. In what order will the 3 2p orbitals be filled? So Hund said that electrons that are in orbitals of the same energy, same subcell, have preferably the same spin. And therefore, that means that if I want to put 3 electrons, I will not put them like 1, 2 here and the 3rd here. No, I will make them to have the same spin, and then the 4th one will go with the opposite spin. This is the 2px, let's say, 2pz and the 2py. 1 electron is going to go in each one of them, and then it will go in the opposite spin. Now let me show you 1 or 2 exercises, and I will make a video after that with more examples on electron configuration. In what order will the following orbitals be completed? You could do them in a monic row, but if you wanted to justify why you do that, we do it on the way of the sum of n plus l. Yes, I'm sorry. So 4d has what sum? 4 plus d is 0, 1, 2. Therefore 4 plus 2, it has a sum of n plus l. This is what I'm writing here. N plus l equals 6, while n is 4. Okay. 4 plus, what is the f? 3, therefore 7. Therefore 4. Then I got 5s. 5 plus 0, therefore 5, and 5. Then I got 5d. 5 plus 2, therefore 7. Well, I'm in the 5 here. And 6s. 6 plus 0 is 6. Well, this is 6. So, I'm starting with the lowest energy, n plus l. This is the 5. So, the lowest will be the 5s I will fill first. What will I fill then? Then I see I have the 6, but I got 2 with the same sum of n plus l. Therefore, which will I fill first? The one with the lowest n number, therefore the 4d. 4d, then I will fill the what? The 6s, and then I got the n plus l sum equal to 7. Which one of these will be completed first, will be filled first? The one with the lowest n number, therefore the 4f, and then the 5d. Yes. Okay? Now, which of the following electron configurations violate Pauli exclusion principle? What did Pauli said? We can't have electrons of the same with the same 4 quantum numbers. Therefore, all electrons must have opposite spin. Therefore, which one violate Pauli's principle? First of all, this one. These 2 electrons are in the same orbital. Therefore, they have the first three quantum numbers the same. And the fourth quantum number, which shows their spin, they have the same spin. They both look upward, therefore they have the same spin. Therefore, these two electrons have what? The same set of quantum numbers. Therefore, this one violates Pauli's exclusion principle. Does that violate Pauli's exclusion principle? No. Does that? No. That? No. Doesn't mean that this is correct. It is not. And we will see right now why. But it does not violate the Pauli exclusion principle. And this again here violates the Pauli's exclusion principle. So A plus Z violate Pauli's exclusion principle. And then, which of these electron configuration violate Hund's rule? Do you remember what Hund said? Hund said that when we fill orbitals, we prefer them to have the same spin. So, this one, it actually violates, because if I were to put 1, 2, 3, 4 electrons in 3 orbitals, and let's say I start with an upward spin, I would put 1, 2, and 3, and then the fourth would be here, but with a downward spin. Therefore, this cannot be correct. Now, if I said I wanted to put the first one with the downward spin, therefore I would have 1, the next ones must be with the same spin, 2, 3, and after I've completed with that spin, then I would start putting with the opposite spin, and therefore the fourth would be like that. Therefore, this violates Hund's rule. Does this violate Hund's rule? No. This is like that, and it's correct. Does this violate Hund's rule? Let's go see. Let's say I want to put 1, 2, 3, 4, 5 electrons in 5 orbitals. Let's say this is a D orbital. It is okay. So I would like to put 1. Let's say I would like to start with an upward spin. 2, 3, 4, 5. Therefore, or 1, if I were to start with the downward spin, 2, 3, 4, 5. So this or this is correct, but this violates Hund's rule because I could have this should be here with an upward spin. Okay, because what Hund says, let me remind you, electrons, that are in orbitals of the same energy have preferably the same spin. This could have the same spin as this, but it does not. Therefore, it violates Hund's rule. Let's go to this. This violates Hund's rule as well. One, 2, 3, 4, 5, 6. So I want to put 6 electrons, which start 1, 2, 3, 5, and 6. Not 5, and then the 6th one would go somewhere, but with an opposite spin. Or if I were to start with a downward spin, 1, 2, 3, 4, 5, and then 6. This is incorrect because it should have been put with the same spin as these ones. Okay, therefore it violates Hund's rule, and this thing violates Pauli's exclusion principle. And these are all for today, guys. Now, I wanted to say 2 things about the chemistry part. I've noticed that in the IMAT many times they require to know some fundamental elements from the periodic table, their names and their atomic numbers. What I would propose you is to learn the first 4 rows of the periodic table, and there's actually a really good song. I'm going to put the link here or in the description in order to learn the first 4 rows of the periodic table. There is no need to hurry. You could just slowly learn them, and it would be great. I have learned them, and they've helped me in the IMATs, in general in the chemistry preparation. They've helped me much. Also, in the next video, I'm going to solve more exercises about electron configuration, because I understand it can be a sensitive subject. It is a really important one for the IMAT. Almost every year they have one question about electron configuration. Therefore, and there are some notes I would like to add also. Okay, thank you guys for watching. Bye bye.